Welcome Poulami Dutta Roy from Chennai Mathematical Institute, India, to give the talk on parametrized tests of GR. You have 30 minutes. I can let you know at 25 or something. So the floor is yours, please, without further ado. Thank you.
Okay. So, hi everyone, and I'm Poulami, and today I will be talking about two aspects of parameterized tests of GR. The first is the extension to 4P and order, and then is the principal component analysis. So, I have divided my talk into three broad parts. First, we will see what are parameterized tests and why should we bother about them, why are they so important. And the first part of the talk is the 4P and extension of these parameterized tests. And depending upon the time we have, then we can go on to the second part, which is the principal component analysis. So, okay, so let us move on to the first question that we ask is, why do we need to test GR? So the first answer to that can be that there is no reason for GR being the fundamental theory of gravity at all scales, at all energy scales. And there could be possible deviations to the GR in the strong field regime. And apart from these obvious answers, there are certain unresolved problems in GR, like the existence of singularities, and there is still no complete quantum theory, and so on. So with these points in mind, we then try to probe how valid GR is as the fundamental theory of gravity. So in this context, gravitational waves come as a very unique probe to test the validity of GR, especially in the strong field regime. And that is what we will be discussing about in this talk. So, So next comes this very familiar picture. I hope everyone is very familiar to this. So this is the gravitational wave signal that comes from the inspiral merger and ring down of a compact binary. So as you can see here that the inspiral part is studied through the post-Newtonian theory. And that is followed by the merger part, which is a very strong gravity regime that is very highly relativistic and can only be studied through numerical relativity. And that is followed by the remnant, which is formed in a perturbed state, and it loses its perturbation through what is called as the ring down. And that is studied through the perturbation theory. So in this talk, we will only focus on the inspiral part of the binary signal, and which is studied through the post-Newtonian analysis. And our aim in this work will be to test the validity of GR through the inspiral signal. So you can test GR through the other segments of the gravitational wave signal as well, like the merger ring down or the whole signal as well. But for now, we will only focus on the inspiral part of the gravitational wave signal. So let us take a look at some of the basics that we would need. So what is the structure of the gravitational wave inspiral phase, and what does the post-Newtonian analysis give us? So to answer that, we start from a very fundamental physics equation, which is the energy balance equation. Now, what does this equation mean is that there are two binaries, compact objects in inspiral with each other, and we assume that they are losing their energy only through the gravitational waves. So then you have on the right hand side the flux of the gravitational wave that is emitted from this process, and that will be equated to the time rate of change of the energy of the system. So if we do this matching of this energy balance on both sides, they can be expanded as a powers of V by C. So as you have already heard in the multiple talks yesterday and today, these energy expressions can be expanded as a power of V by C. So what this means is that in the limit of adiabatic limit, that is V by C is much less than 1, you can expand as a series expansion of this velocity. And then you do a process called the stationary phase approximation. And at the end, you will end up with the waveform of the gravitational wave in the frequency domain. So you get a very simple expression like this, that h of f is the frequency domain waveform with amplitude a of f and a phase factor denoted by phi inspiral. So since we are only focusing on the inspiral part, we are denoting this phase as phi inspiral. And because of this expansion in the post-Newtonian theory, in terms of V by C, you get a structure of the inspiral phase as is shown here. So you have, as you can see, that the phi inspiral can be written as 2 pi f Tc minus phi c. So this Tc and phi c are corresponds to the time of coalescence and phase of the binary. And then you have a series expansion in powers of V. So you can see that there is some coefficient phi k associated to the power of V and phi kl, which is associated with the log terms that comes in the series expansion. So these phi k and phi kl are called the post-Newtonian coefficients. And if we do this series expansion till k taking values from 0 to 7, we get the final form of the inspiral phase. So if you look at the table that is shown on the side, you see all the coefficients that come if we do the expansion in powers of V from V to the power 0 to V to the power 7. And they will correspond to 0 pn to 3.5 pn. So 0 pn is the most fundamental, or sorry, most lowest order Newtonian limit. And that corresponds to V to the power 0. And as you go on to increase the number of terms in the series, you get higher Pn orders with a corresponding coefficient associated with that. So this, so there you can see that there are 8 coefficients, and these all are binary. They have a function of the binary parameters. So binary parameters meaning the masses of the individual binaries, their spins, and so on. And in this expansion, you can also see a parameter eta, which is nothing but the symmetric mass ratio, which is written in terms of the individual masses. And the velocity can be written in terms of frequency once again. So here is what the post-Newtonian theory gives us, that we have an inspiral phase which can be expanded in terms of V. And there corresponds to different coefficients that come at different powers of V. And the beauty here is that because we can expand the phase like this, we are able to study the various physical effects that also come into play at different Pn orders, which we will come back once again later. So now, with this idea, let us see what are parameterized tests of GR. So now we have got the Pn expansion of the inspiral phase, and now we will use that structure to test the validity of GR. Now, how do we do that? So here comes this parameterized phase. So this phi k is the coefficient, and you can change that phi k to a parameterization where phi k GR is the contribution that comes from GR, and there is a fractional deviation associated with it, which is called this delta phi k hat. Now, what this means is that if GR is indeed the true theory of gravity, then we will measure this delta phi k hat to be exactly 0. And if there is any other deviation to it, then we can say that there is a deviation from GR, and the fundamental theory of gravity could be something else as well. So, but to give a summary of this parameterized tests, these are theory agnostic tests. So it means that we can't say what if you do in fact get a non-zero value of this fractional deviation, we won't be able to say what that other theory of gravity is. All we will be able to say is that GR is not right. There is some other theory of gravity at work. And we introduce these deformation parameters only in the inspiral phase. And these are null tests, because if they are 0, then GR is consistent. And they will also help us capture the physics effects that are present at different Pn orders. So now we come to the measurement of these deformation coefficients. So what this means is that when we have a gravitational wave signal, we measure the parameters out of that. The parameters being the mass ratio, spins, and so on. Similarly, we will also measure the deviation coefficients, or these fractional deformation coefficients that we have just introduced. And since we know that there is a detector noise associated with it and so on, we will have a posterior distribution associated with each measurement of the parameter. So you say if I am measuring delta phi hat 0, then I will get a corresponding posterior distribution associated with it, which will correspond to a mean and a median value. Along with it, there will be an associated width to it. So narrower the width of this posterior, the better is the scenario, because I'm able to constrain that parameter value with that much accuracy. So this is regularly done by the LVK collaboration. And as an example, I have shown one of the latest plot from their GWTC3 gravitational wave population of the binaries. And you can see that the different PN orders till 0 to 3.5 PN are shown along with their corresponding bounds. So these bounds correspond to the 90% credibility, and you just need to keep in mind that lower the value of the bound, the better it is, because with that much precision, we are able to measure it. So till now, there has been no deviation of GR detected, and everything is consistent with GR. So now we come to the extension to 4PN order. And this work I have done in collaboration with Shantani Dutt and KG Arun in CMI. So till now, we have seen the phase of the inspiral gravitational wave to be extended to v to the power 7, which corresponds to 3.5 PN term. Now, recently in Luc Blanch's 2023 paper, it has been extended to 4 PN and 4.5 PN. So 4 PN will correspond to v to the power 8, and 4.5 PN will correspond to v to the power 9 terms in the C series expansion. And as you can see that apart from the 3.5 PN terms, now there are more intricate structures to the inspiral phase. And the 4 PN term has a log and log square term, and the 4.5 PN has non-log and log terms. So this is the new structure that is computed recently, and that is taking us to even higher powers of the velocity. So now we are slowly closing into the high velocity regime. So now, along with this extending the inspiral phase to these high velocity powers, we will also take a look at the different physical effects that will come into play in these PN orders. So so you can see that the inspiral phase can be simplified to a structure like this, where this 3.5 PN is the usual 5 frequency contribution till 3.5 PN that we all know of, and that is currently used till now. Now, along with that, recently computed v to the power 8 and v to the power 9 terms are present. So the v to the power 8 term has a log and log square contribution, and the v to the power 9 term has a non-log and a log contribution. So now the physical effects that will come into play, to give a context of that, let us go to the 1.5 PN order. So at 1.5 PN, this tail effect is something that comes into play. What that means is it is a backscattering of the quadrupolar wave from the space-time, or that is generated by the mass m. Similarly, at 2.5 PN, there is something called a memory effect that comes into play. And as you keep on going to higher and higher PN orders, you will keep encountering more and more nonlinear effects. So as an extension, when we go to 4 PN and 4.5 PN, we encounter 3 new nonlinear effects, which are tabulated here. So the first one is the tail of memory, and the interaction term is quoted here. And the next effect is the spin quadrupole tail. And at 4.5 PN, there is an even more nonlinear term called the quartic tail term. So if we do a test of GR at these PN orders, and we do in fact get a deviation, then we can say that these physical effects are not enough. There might be some other physical effects which are coming into play at these higher PN orders. So that kind of gives highlights the importance of these parametrized tests at these high PN orders. So now we want to do the test of GR at 4 and 4.5 PN. So what this means is now we have these 4 new terms in the inspiral phase apart from the 3.5 PN, and we will do this introduction of this fractional deviation parameter and try to measure them. So till now we had from phi 0 to phi 7, and correspondingly we had the deviation parameters. Now, because of these 4 new terms at 4 PN and 4.5 PN, we got 4 new deviation parameters. So this delta phi 8L hat corresponds to the 4 PN log term. Similarly, this delta phi 8L square corresponds to the 4 PN log square term, and so on. So in total, we get 4 new deviation coefficients, and that we want to estimate that how their projected bounds are going to be in use for the future gravitational wave detectors. Now, in order to compute these bounds, we will be using the Fisher information matrix. So which is a very standard tool that is used in parameter estimation, and it gives the projected bounds on the parameters. So without going into too much of details of the process, all I want to show here is each element of this Fisher information matrix is denoted like this. So gamma AP is one element of that matrix, which has information about the waveform, which is denoted by H tilde, and the waveform is taken derivative with respect to A and B. A and B basically the parameters of my parameter space. And this SNF is the noise power spectral density, which changes from detector to detector. So whatever you choose as the detector of interest, accordingly your SNF will change. So this is what the Fisher information matrix looks like, and we will be using that to get the bounds. And for this analysis, I have used the AMR phenom-D waveform, including the new phasing terms, and this is a single parameter test. So I have highlighted the single parameter test because if you see the parameter space, you can see that the usual the luminosity distance, TC, phi c, and all of these are the usual parameters that you would measure from a gravitational wave signal. Along with that, we have the delta phi k hat, and only one of the parameters is coming at a time. So if I want to measure 4 of the new deviation parameters, I have to do this single parameter test 4 times, with each time having one of the delta phi k hat that I want to measure. And for this study, we have used the sensitivity of the advanced LIGO and Cosmic Explorer and LISA. So now let us see some numbers. So in this table, we see the bounds on all the deviation coefficients starting from 0 to 4.5 pn, and we have taken 2 sample binaries. So the first binary is a heavy mass system, GW150914 light, and their masses of the components are 35 plus 30, so it's a heavy mass system. And the 151226 light is a smaller or lighter mass binary, having masses 13 and 7 solar mass. And we have tabulated all the bounds, how they are going to be for a sensitivity of advanced light. So now what we want to know is what are the bounds that are going to be of these 4 new deviation parameters for a wider parameter space. Like say if I vary the mass of the binary or the mass ratio of the binary, how are the bounds going to vary? So that is summarized in this plot. So here in this plot, we show the bound on these parameters delta phi 8L, delta phi 8L square, and the 4pn deviation terms for the different detectors, advanced LIGO, CE, and LISA. And here you can see that the x-axis is where the total mass of the binary is varying, and the different colors of the plots correspond to the mass ratio. So Q equal to 1.2 is a very symmetric system, and Q equal to 10 is highly asymmetric. Now you can see that depending upon the parameter that we are trying to study, the bounds are changed. And as I have mentioned previously, the lower the value of the bound, the better it is. So we can see that out of all of these 4 parameters, delta phi 8L hat has the best bound, because you can see that the plot goes to 10 to the power minus 3. So for this case, we can constrain this parameter with that much accuracy. In comparison, you can see that the other bounds are going to order of 10 to the power minus 1 or 10 to the power 0 and so on. Now, if you consider the behavior of the individual detectors, you can see that LISA is giving the best bound. So that is that can be attributed to the long in-spiral signal that is observed in LISA. So for any of the parameters, LISA is going to give you the best bound. Now, if you take just one of the parameters and study the dependence on the mass ratio Q, we see that delta phi 8L and the 4.5 pn deviation parameters have the worst bound for the symmetric. So this you see that the blue curve in all of them is at the top, and a better constraint is obtained for the more asymmetric system. So this is because it is dominated by the odd multipoles. In comparison, if we see the delta phi 8L square, we have the better bound for the symmetric case, which can be attributed to the dominance of the even parity. So this I have summarized in this slide, where we have studied the different bounds and why are some of the bounds more prominent for the asymmetric binaries, and why for 4pn log term we get a better bound for the symmetric system. Now, the takeaway message is that the best constraints are obtained for the 4pn log term, that is delta phi 8L. And the order of that bound is 10 to the power minus 3 for Lisa, minus 2 for C, and minus 1 for advanced light. And as I have already mentioned, the supermassive black holes that are observed in the Lisa band will give the best bound on all of the deviation parameters. So the 4pn log square and the 4.5pn has a bound of 10 to the power minus 2, and the 4.5pn log term has the worst bound of 10 to the power minus 1. So now comes the second part of the talk, which is the principal component analysis. And here are the names of my collaborators who have worked in this project. So till now, we talked about the single parameter test. Now we will shift to something called multi-parameter test and see why are they important. So for now, let us just keep in mind the 3.5pn phase and not bother so much about the 4 and 4.5pn terms. So in the single parameters test, as I have mentioned previously, that apart from the usual GR parameters, we take one deviation parameter at a time. Now, when we go to multi-parameter test, we will be measuring all the PN deviation parameters at the same time. Now, why is it important is because any alternate theory of gravity might introduce the deviation at multiple PN orders. So if I measure one parameter at a time, that is not the right way to do it. We need to measure them all at the same time because they can be introduced at any PN order which is not known to us. And also, any deviation observed in single parameter test cannot be uniquely attributed to possible modification only at that PN order. So because of these two reasons, we are hugely motivated to use a multi-parameter test. That is, measure all of the deviation parameters at the same time. But there is a catch. The problem is that when we do the multi-parameter test, there comes these correlations between the parameters, which is going to mess up the measurement, and they will not allow a very good bound or a very good measurement of the individual deviation parameters. And the current gravitational wave detector sensitivity is not at all enough to lift these correlations, and hence we will end up with the uninformative posterior. So that means that we will not be able to measure these deviation parameters with very good accuracy if we do a multi-parameter test. Now, the solution to this scenario can be through performing PCA. So the basic idea of this principal component analysis is a basis change. So you have these deviation parameters and you go to a different basis of PCA. And here you can see that rest of the parameter space is still remaining the same. Only these deviation parameters are now shifted to a different basis. And these PCA bases can be expanded as a linear combinations of the original deviation parameters. So we need to perform PCA to identify the best measured linear combinations of the deformation parameters. And after doing this, what we will get is this new basis of PCA parameters, which will have very less correlation, and hence they can be measured very accurately in comparison to the original delta phi k hats. Now, as a proof of idea, here we see the two corner plots between the original and the PCA basis, and we do a comparison. So here we see that these delta phi k are varying along with their posteriors and their correlations. So you can see that the posteriors are very bad. Some of them are very wide and they are not at all informative. So that is not good. That is what the correlations are doing, that they are not letting us do a very good measurement of these original delta phi k. And if you see at the correlation that is shown in these contour plots, you can see that the contour plot is also white bursts. So if they are uncorrelated, then we will be seeing a circle here. But you can see that it's all messed up for the original delta phi k. But if we take a look at PCA and focus only on the first two PCA parameters, say, then we see that the posterior is actually very nice, and the bounds on the posterior and the width of the posterior is quite narrow. So since this is a GR waveform, the mean of the deviation is also at 0, showing that GR is indeed being recovered, and the correlation between these PCA 1 and 2 is also 0. which means that there is no correlation between PCA1 and PCA2. So that is what we always wanted, that we wanted to measure the deviation parameters with very good precision, and also reduce the correlations. And PCA is doing that job. Now, you can ask that why the other PCA parameters are not doing that, because most of the information is captured by the first and the second PCA. And as you go to higher PCA terms, the less information they are carrying, and hence they are resulting in a more uninformative postage. So we will only be interested only in the first two PCA and try to see the results. So now we have done this analysis for multiple injection cases where we have taken the binary black hole waveform for aligned spins, which are consistent with GR, with precessing waveforms, which are once again consistent with GR, and also with non-GR waveforms, where we have by hand put these deformation parameters to be not non-zero values, which will correspond to the non-GR waveforms. And we have seen that in all these cases, PCR recovers the injected value quite well. So in essence, PCA works. So with that, I will summarize the results that we have discussed. So we now know what are parameterized tests of GR, that are the theory agnostic tests that only use the in-spiral phase of the gravitational wave. And we first discussed the single parameter test, which we extended to 4.5 PN by introducing 4 new deviation parameters at 4 and 4.5 PN of the in-spiral phase. And we saw that how good the bounds can be, and the best bounds were obtained for the LISA band. And then we saw the necessity of the multi-parameter test and why they are problematic as well. And to resolve the scenario, we saw that PCA can be applied and PCA works well for GR and non-GR injections. So that's it. Thank you.
Thank you, Poulami, for the very nice talk. There's time for a couple of questions. Please either raise your hand or speak directly on the microphone or chat. Yes, Sailesh, please go ahead and ask your question.
Yeah, thanks. Thanks for the nice talk. So I have just a clarification regarding this. Like, are you planning to take like black hole background as well for testing these? Like, if you take the higher order PN, 2 PN, 3 PN, so it's not very straightforward to generate the waveform even, because I mean, given a background, as far as I know from the existing literature, that there are some there are some issues, like the precise development probably has not been done if you take the higher order PN corrections given a black hole background. So are you planning to take any black hole background as well?
I'm not so sure what you mean. So we
So
are
suppose,
doing
so
everything in GR, right? So for GR,
yeah, that's
everything
fine.
is calculated. Uh-huh.
So my point is, suppose, I mean, for a particular, so okay, so let me just restate the question. If you might have seen a paper by like Johansson space-time or Ken Tyagi, where a general deformed curve geometry is there, right? So there are
Mm-hmm.
several parameters are sitting that can be mapped to I mean, many non-GR theories, right? So if you
Mm.
consider a particular like those parameters, if you're taking a particular theory, so you can map those parameters to that theory and you can do the analysis. That is fine. But I'm saying, if you keep these parameters, the parameters which are sitting in the deformed curve geometry, that is space-time. So whether I mean, now this is a background, right? Black hole background. So you're not considering a particular theory. These are containing various deformation parameters. So so in that sense, I'm saying that can we can we have the
Uh,
like full waveform we can generate, whether uh, considering a general black hole background containing deformation parameters that can be mapped to any other
See,
space times?
there are some works that try to relate these fractional deformation to modified theories of gravity, and like for example, as I have shown in this, let me go to this plot. So
But
you can see that there
I
is
guess, yeah, yeah.
Yeah, so this is all a null test, and that is the test of the general theory of relativity. Like we don't bother about the yeah. So we want to test whether GR is valid or not, or there is some modified theory at play or not. So if that is all we want to do through the null test, and that's what I said, that they are theory agnostic. So we can't say also if there is other theory of gravity, if in fact we do get a deviation. So like at -1 pn and 0.5 pn, there is no term in GR that corresponds to -1 pn and 0.5 pn. And if we go to scalar tensor theory, like yesterday Laura said, then you have the -1 pn and 0.5 pn. So in other theories of gravity, you can have different pn orders, but currently we all want to do is constrain these deformation coefficients and try to see if there is any other deviation from GR. That's
I see. I see.
Thank you. Thanks, Poulami. Any other questions for the speaker? I have a very quick question, maybe a naive question. When you have the log V term, I was thinking whenever you have a log, there should be a scale, right? Like log V over V naught or something like that. Maybe you set it to 1. So I was just wondering if it has any effect in whatever you're doing. The scale of
so velocity we are writing it. Let me go back. So V is we are writing as pi mf, and this is a dimensionless term. So mass we are writing in terms of frequency inverse. So everything is done.
Okay, so it's the V here is a dimensionless quantity, right?
Yes. Yes. Yes.
Perfect. Thank you so much. Any other questions? Quick questions? Okay, if not, let's thank Poulami once again for the very nice talk, and thank you. And let's